Chapter 1, slides 10 through 25. So we're going to start talking about the structure of an atom. So this is a review from general chemistry. Atoms are made up of protons, neutrons, and electrons. Okay, so in the nucleus, we have the protons and the neutrons. So the nucleus contains positively charged protons and neutrally or zero charged neutrons. So overall, the charge of the nucleus, because it has protons, which are positively charged, is overall positive. Now, the mass of an atom, of any element, is largely comprised of the protons and the neutrons because they amount to about 18 times the mass, right? They are so much heavier than one electron. The weight of an electron, the mass of an electron, is insignificant compared to the mass of a proton or a neutron. Therefore, we kind of don't worry about it, right? Electrons are negatively charged. And the electrons are what take part in chemical bonding and thus the reaction. So although the protons and the neutrons are the most part of mass in the atom, it's actually a very, very, very small space. You can liken it to a baseball field. The size, despite the mass, of the nucleus is about the size of a pea if you set it at home plate. And the size of the electron cloud, where the electrons reside with minimal mass, is the size of the stadium. So we're going to be looking at the stadium despite the fact that the mass is not significant. Isotopes are different types of the element whereby the protons remain the same. So just remember that what makes an element, what makes oxygen, is the fact that it has 8 protons. What makes hydrogen is the fact that it has 1 proton. Protons cannot change unless you're actually talking about a different element. That's what makes it the element. Neutrons and electrons, though, can vary. When the neutrons vary, we call this isotopes of an element. And because the neutrons weigh something significant, different isotopes have different masses. So isotopes are atoms with the same number of protons, but different number of neutrons. Mass number is the sum of the protons and the neutrons in an atom. What's the difference between mass number and atomic weight? Well, atomic weight takes into account all of the different types of isotopes that occur in nature. So if you have 99% of one type of isotope with a mass number and 1% of a different isotope of a different mass, they're weighted and you get a new atomic weight where it factors in the weight of each isotope and their abundance. But mass number is just looking at your standard number of protons or neutrons for one given isotope. So I'm showing here oxygen and 3 of its existing isotopes and showing you that the O16, oxygen with the atomic mass of 16, is the one that's the most abundant, 99.762% naturally occurring. So when you look at the weight, that's why the atomic weight is so close to the 16 mark. Okay, just a quick review of some terms from Gen Chem. Atomic number is the number of protons in the nucleus for any given atom. And you see this above the elemental symbol on the periodic table. So that's a quick reference. Mass number, as we just discussed, is just for any given isotope, it's the sum of its protons and neutrons. Isotopes have the same atomic number, but different mass. Atomic weight takes into account all the isotopes and their weights, but also how naturally abundant they are. And molecular weight is the sum of atomic weights for all atoms in a molecule. We're going to be using the periodic table and periodicity a lot. As I mentioned in the previous video, we're doing a lot of qualitative assessments for reactions. And so we're going to need the periodic table and understand what it's telling us as a tool. It's the only tool you're allowed to have on your exams, and you should be able to understand what it's telling you. There's a lot of information in the periodic table. So I just wanted to make sure that we were all clear on what all of these things are for a given square. Okay, so there we got the basics about an atom down. Now I want to talk about Lewis structure as we lead into bonding. So in 1915, Lewis proposed that a filled shell of electrons is especially stable. So now we're talking about an atom, and we're talking about its orbitals. And when its outermost orbitals are filled, have as many electrons as possible, this is especially stable. So that's the first premise. The second, that atoms will transfer or share electrons in such a way as to attain this filled state. So this is going to propel a lot of the whys, right? The why questions we're going to ask ourselves during this course. Well, why did that happen? Why does this happen? A lot of it stems from these two premises. A filled shell of electrons is the electron configuration of a noble gas, right? The noble gas has absolutely no desire to attain any more electrons because its outermost shell is full. So examples of noble gases, right? You look all the way to the right on the periodic table and you see things like neon and argon and even helium, right? And helium is an interesting one because it's got only one shell and it's very tiny. And this is probably the only one that doesn't, by virtue of the name, follow the octet rule in name only. But it follows the rules set up above, number 1 and 2. But I want to take this moment in discussing filled outer shells to talk about this octet rule. We use this term a lot, and it means, in a very general sense, again, helium could be the exception, but it really does, it's not an exception given that it follows premise 1 and 2 above. But this principle is called the octet rule because a filled shell implies 8 valence electrons. Now, helium's so small, it couldn't have 8 valence electrons. Its maximum is 2. But because it reaches its maximum, it does technically meet the octet rule. But that's where the octet rule name comes from. Let's start with ionic bonding. Ionic bonding is when you have an atom that would more likely want to give up an electron and another atom who would much rather like to gain an electron. Typically, the electron exchange could be 1 electron or 2 electrons. Those are the most common that we're going to see, the most prevalent in this course. And that leaves the 2 atoms with formal charges. So let's go over an example together. Using the octet rule, or the premise that atoms' desires are to have a filled outer shell, if we look at the outer shell for lithium, its outermost shell is shell number 2. Think of it like an onion. You know, the closest numbered shell is towards the nucleus, and then it has another shell and building outward. So it's the highest shell number is 2. And it's the most outer shell, and it only has 1 electron in it. And the octet rule tells us that it would rather have 8. So it's really tough to find 7 donated electrons. It's a lot of energy to pull in those electrons. So the easiest thing for lithium to do is to get rid of that electron in the outermost shell so that its new outer shell is shell 1 and it's filled with its 2 electrons. Shell 1 is the only shell where the octet rule is 2. Right? So that's like helium, right, is an example. It's a noble gas because its outer shell, which is shell 1, is full. 2. All the other ones, right? Once you start having shells 2, 3, 4, 5, then its outermost shells will be following the octet rule because they'll be desiring 8. All right, let's take a look at fluorine. Fluorine's outer shell is also 2. It's got lots of different types of orbitals making up that shell, but altogether, if you count them up, there's 2 in S, 1, 2, this P has got 2, the next P's got 2, and then 1. So 2, 4, 6, plus the 1 is 7. 7 total electrons in shell number 2. Well, the easiest thing to reach an octet in this case is to gain 1 electron. So lithium and fluorine coming together, exchanging electron, everyone gets what they want. Lithium dumps the electron so that its outer shell is now 1s and it's filled. Yay. And fluorine gains this electron, right, filling the outer shell 2. Now it has 8 electrons and it's happy. So this is a win-win scenario. When there's an actual exchange, giving and taking, this is an ionic bond. These tend to happen on the periodic table between the elements far to the left and the elements far to the right. Let's just exclude the noble gases because they're happy already. Now, some ways that we represent ionic bonding is either with the formal charge, right? As you can see, if you lose an electron, overall, your charge is going to be positive. And if you gain an electron, your overall charge will be negative. So sometimes you'll actually see people write the formal charges of ionic structures, and other times not so much. The most common way to write lithium fluoride salt is LiF. You're all familiar with the most common salt, table salt, NaCl. And we see it written NaCl all the time, despite there actually being positive to the sodium, -1 to the chlorine, because there was an actual exchange. What we don't like to see is when people draw a line between the lithium and the fluorine, because we're going to save that as an indication for sharing of electrons. And that's not what's happening here. Electrons are what we're going to be focusing on, and so it's really important to be able to draw molecules and understand meaning. The easiest way to identify ionic compounds is to look at what the atoms are in the system, okay? So if you see any group 1 or group 2 atoms, these are things like sodium, lithium, right, far to the left. These are metals that only have 1 or 2 electrons in its valence shell. So they're more susceptible to giving. Thus, when you have a molecule and you see one of these group 1 or group 2 atoms present, then, oof, you're like, that is probably an ionic compound. And you right there and then you can start attributing charges and understanding how it's going to behave in the chemistry that you're looking at. So I really want you to be able to identify a molecule as ionic or covalent. And that's what we're working towards right now. Some organic molecules contain ionic bonds. So for example, methyl ammonium chloride, which is shown here on the left, you can see that it's got a carbon in it, so it's organic. The nitrogen that it's attached to has a formal plus charge, and there's a counter ion with a chlorine minus nearby. This is not written where the nitrogen and the chlorine are bonded. If it was written like that, if you counted the electron pairs, the lines, around the nitrogen, representing covalent bonds, then it would have more than 8 electrons around it, and that would exceed its octet and isn't possible. So let's talk about covalent bonding, since this is going to be at the forefront of our discussions. When electrons are shared between atoms, this is called a covalent bond. So it's not an exchange, we're now sharing, okay? If you are sitting on the couch and you are sharing a blanket with the person next to you, there are different ways of sharing that blanket, right? Sometimes people are blanket hogs and most of the blankets are over on their side. Even though it's still technically slightly covering you and you're sharing it, there's an imbalance, okay? We're going to talk about these types of imbalances. Sometimes covalent bonding is perfect sharing. Sometimes someone's hogging the blankets a little bit more, hogging the electrons a little bit more than the other. And we're going to talk about those nuances. But in order to obtain the octet, covalent bonding can ensue and afford us that win-win situation, because sometimes it's not just as easy as giving one electron here and taking an electron there. So what we're going to do is we're going to look at situations like carbon per se, where you have the outer electron valence shell number 2, and it doesn't have that easy to decipher how to get to an octet scenario. If you count how many electrons, you see that it has 4 valence electrons. It's right in the middle, right? And you're like, well, do you gain 4 or do you lose 4? What's the easiest thing to do? Well, neither is good. So the best case scenario for carbon is to create a relationship with other atoms around it in a sharing scenario. One thing that it loves to share electrons with is hydrogen. Hydrogen's outer shell is 1. Remember, 1 is the exception type, technical exception to the octet rule, although it follows Lewis's premises, where it has 1 electron and its octet rule would be 2. It wants 1 more electron. And so what we can do is we can bond carbon 4 times with a hydrogen in order to obtain this carbon with 4 hydrogens around it over here on the right-hand side. So when I write a bond, a covalent bond, I'm going to use a stick. And the stick represents 2 electrons. So as training wheels, let's just remind ourselves that that stick really does represent 2 electrons. And although I write it right in the middle, kind of equidistant from one another, understand that covalent bonds are not, when you're sharing, it doesn't necessarily mean equal sharing, okay? Sometimes it may, other times it does not. So what you're seeing here is a relationship. In order for everyone to be happy, they share the electrons around them. So every single bond represents 2 electrons, and a covalent bond gets to be counted by each atom. So if you were looking at the hydrogen on the left has a covalent bond, and whatever it's got next to it, it's got this 1 bond, it gets to count it for itself. So it counts the 2 for itself and it's happy. You can do that for every single hydrogen. This hydrogen's happy, this hydrogen's happy. They all have 2 electrons because they all are involved in a covalent bond. And when you look at the carbon also, because it's sharing, they're sharing the load, the carbon gets to count all the electrons. So if you count every bond, and every bond is 2 electrons, it has its 8 electrons, octet, and it's happy. So this sharing scenario is beneficial to all the atoms involved. One way to symbolize these types of covalent bonding is through Lewis dot structures. In a Lewis dot structure, each valence electron is symbolized by a dot, and it can be written like so. Now this is the way that I'm preferring it. I like the sticks rather than the dots. We're going to use these dots to represent lone pairs of electrons that are not involved in a covalent bond. And Lewis dot structure will still allow us to do that. But this is how I want you guys to begin to get comfortable drawing Lewis dot structures. So one of the retrieval cues that I need you to understand is how to look at valence electrons. So you'll always have a periodic table at your disposal. And the easiest way to do this is to just forget the transition state metals and focus on the groups 1 and 2, right? Remember, those are the ones that if you see any of those, you're thinking, ooh, it's an ionic bond. And then you can just skip across and start with the boron, carbon, nitrogen, oxygen, fluorine rows, and start continuing counting from there. 3, 4, 5, 6, 7, 8. So if you have a periodic table, you can always do 1, 2, skip all the transition metals, and continue 3 to 8. If you were wondering about a particular atom, say carbon, and you wondered how many valence electrons it has, you simply, if you've numbered it, you simply look above at its group number and see that it's in group 4. All right, it has 4 valence electrons. So it becomes faster and easier for you to make that assessment. So please get comfortable with identifying how many valence electrons an atom has. Valence electrons are going to be the first way you'll become comfortable with bond trends. So valence electrons are not shared between two atoms, are called non-bonding electrons. A pair of non-bonding electrons is called a lone pair, and this is what we're going to be calling it. I will call them lone pairs. So if I were to draw a Lewis dot structure for methylamine, that's carbon with a hydrogen and another hydrogen and one below. So I'm redrawing what you see up above. The carbon is covalently bonded to the nitrogen, another nitrogen, another hydrogen, and there it is. That's the lone pair. Notice that lone pair is not bonded to anything, but I want to draw it in because it's there, and it needs to be there, otherwise the nitrogen doesn't have an octet. So it's important to draw. We'll see this again in methanol. So if I redraw this into a better looking Lewis dot structure, we can replace the dots with the line bonds for the carbon and 3 hydrogens. The carbon is bonded to the oxygen, which also is bonded to a hydrogen. And you'll notice that it also has 2 lone pairs. We draw water so often, and we forget sometimes to draw those lone pairs, but they're going to be very important. So a Lewis dot structure, a correct Lewis dot structure, must show lone pairs. So when you're doing your homework and you're asked to draw a Lewis dot structure, don't forget the lone pairs or you'll be marked incorrect. Chloromethane, same way. Here's the carbon with 3 hydrogens, so I'm translating what I see up above. The carbon is connected via a bond to the chlorine, and the chlorine has, in this case, 3 lone pairs. But notice that the lone pairs are necessary again in order to express the octet rule for each of those given atoms. Count around each of those atoms. There is no formal charge on any of these atoms, and thus no formal charge on any of these molecules, because everybody's happy. Everyone has an octet. So I need you to be able to understand what a Lewis dot structure is and start practicing the drawing of Lewis dot structures. I'm going to just do this water one with you because you're all very familiar with water, and to show you that you need to remember to draw the lone pairs. So I'm going to let you practice the CH4, NH3, and Cl2 on your own. Now, one of the things that you may wonder is, well, how do I figure out how to orient all of these atoms? Well, one way that you can do that is if you know the valence electrons. So let's work out this water again. If you know how many valence electrons oxygen has, if you look back at the periodic table and you say oxygen has 6 valence electrons because it's in group 6, okay? Oxygen has 6 valence electrons. So this is where the periodic table is going to be able to help you. 1, 2, 3, 4, 5, 6. So if you draw the valence electrons, almost like it was a box, right? Here's the oxygen, 1, 2, 3, 4, 5, 6. So you use as if the atom was in a box, you use the sides, okay? So I'm gonna erase this, but you treat it like it's in a box in a sense, and you use it to put the valence electrons as if they were around a side. So you just keep going round and round. So this is what oxygen looks like. Notice that in order to achieve an octet, it only needs one other electron that it doesn't have, so that has to be brought in by somebody else. One other electron that it doesn't have needs to be brought in by someone else. Once that happens, the oxygen's full. It's reached its 8 electron capacity. But notice that because of its valence electrons, it still has those 2 lone pairs. So you can see that the blue and the red electrons that I drew can be rewritten as a bond line, and the other 2 can be written as a bond line. And that's how we got the 2 bonded hydrogens and the 2 lone pairs. So try that for CH4, NH3, and Cl2. Start with drawing the carbon, the nitrogen, and the chlorine as the atom with its valence electrons around it, and see if you can use the remaining atoms to make bonds, and also show the lone pairs that you didn't need to use. So that is for just single bonds. What about multiple bonds? The sharing of one pair of electrons between 2 atoms is called a single bond, and that's what we've been doing. We also can have double bonds and triple covalent bonds between the same 2 atoms, okay? So here's an example of ethylene, and it's drawn below. Again, count the electrons around the carbon. You'll notice that there are 8 electrons. So each one of those atoms meets the octet rule. Now, it looks like the formaldehyde drawn accounts for all the bonds, but let me just draw in its lone pairs, right? Because these 2 lone pairs hadn't been represented in the Lewis dot structure below. Same goes for the formaldamine. The nitrogen is missing its lone pair, which is right here. All the others are lines representing the bond. And acetylene, far to the right, that one looks good. The carbons, the hydrogens, everybody's in their octet. So notice that you can have 2 atoms with multiple bonds between them, multiple covalent bonds between them. How else can a structure of a compound be represented? We will use Lewis dot structures, but there are also other ways to represent a molecule. One of them being Kekule structures. And as you can see, these are as written. And what you'll notice is that they look just like Lewis dot structures, except they presume that you know that the lone pairs exist. So if you look at the first one, you'll see that there is a bromine here, and if it was a Lewis dot structure, you would show those 3 lone pairs around the bromine. But because this is a Kekule structure, they presume you already know that those are there, so they don't write them. Same thing with the second molecule. The oxygen in the middle should have 2 lone pairs there. And this isn't a wrong way to draw it, it's just a faster, quicker way, because as you'll see in this course, we are so fast in writing large molecules. And if you think about really big molecules, having to write every lone pair is a very, job intensive task to do. And we know they're there. If they weren't there, there would be a charge associated with that oxygen because it wouldn't have an octet. So as you get more comfortable with bond trends, you can start shorthanding down to Kekule structures. Condensed structures are what you pretty much used in general chemistry, and I will very rarely, if ever, use condensed structure. The only time a condensed structure is decent is when the molecule is very small. So, N2 is a very easy condensed structure because there's really only one way to write N2. If I use Kekule structures, as in the previous case, you'll notice that hydrogens are also included. And as the molecules get bigger and bigger, this task becomes a little bit more onerous, as I mentioned. So what we want to do is start representing molecules using skeletal structures. This combines Kekule structures, where we don't necessarily write the lone pairs, but we also do one more thing. We also stop writing hydrogens. Hydrogens tend to be the placeholder on carbons when the carbon has an octet and the carbon is bound to an oxygen or a nitrogen. We have to write those bonds in, but we don't necessarily have to fill in the blanks to make the octet on the carbon with all the remaining hydrogens. So if we don't have a formal charge written and we only show the important bonds, we presume that octets are met on all of the carbons with hydrogens. And we only do this for carbon. We only use presumed hydrogens on carbon. So what this means is that Ns and bens indicate that a carbon is present. So we're actually not even writing the carbon either. And then, in order to satisfy octets, all hydrogens not drawn are assumed. This critical skill is where you guys will become more and more familiar, but it'll feel a little difficult at first, but trust me, you'll get used to it. So what I'm showing here is this 6 carbon, C6, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This C6H12 can be redrawn as a skeletal structure using Ns and bens and presumed hydrogens. You can try transferring or translating these remaining 2 compounds that are drawn in Kekule form into skeletal structures. A little on structural theory. So now that we have some ways of drawing molecules, I wanted to discuss why it's important to draw molecules and really not use condensed structures like the ones on the bottom. In the mid-1800s or so, it was suggested that substances were defined by a specific arrangement of atoms. And that might feel obvious to us given what we know now, but it wasn't back then. And so we can't just look at the formula and say, oh, it's got 6 carbons and 12 hydrogens, because there's probably a lot of different ways of putting those pieces together. Imagine me giving you a set of Lego, and I give your friend the same set of Lego, and you're in different rooms, and I ask you to put them together however you want, right? You guys are probably not going to form the exact same structure. So the term that we use for this, when you're given the same building block pieces or the same atoms, but you are orienting that same set differently, these are called isomers. And there's actually different types of isomers. The first one we're talking about right now are called constitutional isomers. And I'm gonna, in future chapters, we're gonna talk more in depth about these. But here's an example. If I have a C2, H6, O, you could say that each one of these is a C2, H6O, but they're oriented in a very, very different way. If you look at the first way, called dimethyl ether, it has a boiling point of -23 degrees and was classically used back in the day as something to put you out before a surgery. right? So it was sort of the mother of anesthesiology. The other, ethanol, clearly different, has an alcohol group, an OH at the end, rather than the oxygen being flanked by the carbons, and has a boiling point of 78.4 degrees. And as we know, ethanol is in spirits. So very, very different molecules, very different functions. And so we don't get very much information from knowing just the condensed formula. Writing out the structural formula is so much easier to convey information. The atoms that are the most commonly used in this course, apart from carbon, include nitrogen, oxygen, hydrogen, and the halogens. And with some exceptions, each element generally forms a specific number of bonds with other atoms. This is probably one of the first and most important retrieval cues for you, called bonding patterns. And I've alluded to this a little bit. I want you to become very familiar for those atoms. What is normal, right? What is typical? The way that you can train yourself, or the training wheels for yourself, to get used to bonding patterns and to spot them, it might feel memorized at first, but first of all, look at the periodic table. Identify the valence electrons for each of these atoms. Okay, we start with carbon. Valence electrons is 4. If you look at the periodic table, you'll see 4 valence electrons. Nitrogen is 1 next door, has 5 valence electrons. Oxygen has 6, and the halogens have 7. Hydrogen has 1. Okay, so if I know that, then what I can do is say carbon has 4 valence electrons. And I do that little trick I showed you earlier. I draw the 4 valence electrons like the carbons in a box. I just go round and then I fill again if I need to. But if you look, after filling carbon 1, 2, 3, 4 with an electron, you see that it is not happy, and therefore it needs to have 4 bonds. It needs 4 other shared partners. Nitrogen, the bond trend that we're going to see, 1, 2, 3, 4, 5, you'll see that it needs a bond here, a bond here, and a bond here. But I don't need another bond on that other side. It's just simply a lone pair. And if I were to draw in that lone pair, it would just be, I just draw it right there. So to be complete in a Lewis dot structure form, I need to draw that lone pair in there. Notice that carbon didn't need the lone pair. How about oxygen? Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. So we can see that it needs 2 bonds. And it has 2 lone pairs remaining. So I could draw those lone pairs into the structure here. So these are the typical bond trends. And when you see these atoms in their bond trend, there is no formal charge attributed. They're happy, they've got their octet, and life is good. Let's look at hydrogen. Hydrogen has 1 valence electron. Therefore, it's only ever going to have 1 bond and no lone pairs. So it's as written, it's fine. How about the halogens? Fluorine, chlorine, bromine, iodine. For all the halogens, it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Well, it just needs 1 bond. Therefore, it has 3 lone pairs. So to be complete, we have to draw the 3 lone pairs if I wanted to do a Lewis dot structure. Please get very comfortable with knowing if you get stuck because I can't remember what the bond trend is for that atom, this is how you can figure it out. You will slowly tear away at these training wheels and you'll just get very used to bond trends, especially for carbon. Carbon has 4 bonds. If you ever see carbon with 5 bonds, someone has made a very, very, very bad mistake.